Picture a scenario with nothing. It looks blank, doesn't it? But if you look at our universe, you'll find stars, planets, protoplanets, exoplanets, galaxies, and so much more. But to think all of this came from nothing is quite absurd. We know of the Big Bang explosion that took place 13.8 billion years ago, but we don't really know what was before it. Was there nothing before the Big Bang explosion took place? Was the entire universe created from nothing? In today's episode, we will be telling you what we know, so stay tuned. This is a difficult and hard topic to discuss. What existed before the cosmos that we know so well today? Our knowledge of this complex issue is largely hypothetical. We still don't know what occurred before the singularity that created our cosmos. If you are interested to learn about the birth of the universe, feel free to watch The Birth of Our Universe Explained on this channel. Life in the universe began to exist at some point. Was it just because of an ideal situation? Or was it a common event taking place all throughout the universe? It had to have originated from something. How can we know whether our universe is the entirety of something or only a portion of it? The concept of before as a whole seems to be more complex than it seems. But let's go all the way back to the beginning of our universe, around 14 billion years ago, before we go completely crazy trying to figure out the answer to this fantastic question. The time before time. A small, immensely dense ball of substance existed in the beginning. The atoms, molecules, stars, and galaxies that we see today were created when everything suddenly went boom. Or at least that's what scientists have been telling us for the past few decades. However, recent advances in theoretical physics have shown a potential window into the very early cosmos, suggesting that it may not actually be very early at all. Instead, it may simply be the most recent instance of a bang-bounce cycle, or the Big Bounce theory, that has occurred at least once and potentially forever. Of course, these theoretical hypotheses must withstand an array of observational testing before physicists decide to abandon the whole Big Bang theory in favor of a bang-bounce cycle. The Big Bang Theory, which we all know quite well, gives scientists a pretty solid idea of the very early cosmos. According to this theory, the universe was much smaller, hotter, and denser long ago than it is today. All the components that make us who we are were created in that early firestorm 13.8 billion years ago during the course of just a dozen minutes. According to this theory, our universe, which includes all of the stars, galaxies, and everything else, was once the size of a peach and had a temperature of more than a quadrillion degrees. Astronomers have also discovered what may have occurred before the Big Bang. From monitoring the electromagnetic radiation left over from the early cosmos to calculating the amount of the lightest atoms. This is how the universe was born out of nothing. The quantum world of atoms. Astronomers are calling this quantum cosmology. But what is it? The quest to create a quantum theory of the universe is known as quantum cosmology. This approach makes an effort to address unresolved issues in orthodox physical cosmology, particularly those related to the early cosmos. The general theory of relativity, often known as GR or GTR, is the foundation of classical cosmology and provides a remarkably accurate description of the history of the universe as long as you don't discuss the Big Bang. However, the theory falls short of providing what is necessary for a definitive explanation of space and time in relation to the gravitational singularity and Planck time. Therefore, to make this theory have a common ground, you would require a quantum theory with relativity theory. Take, for example, a fallen tree. Maybe a vicious storm knocked the tree down. Or maybe it was cut down by a chainsaw-wielding madman. In the world that we observe around us, all effects must have a cause. The case may be different, though, if you try to understand the Big Bang with quantum cosmology. We have previously said that for every effect, there should be a cause. But in the quantum world, effects can occur without any cause whatsoever. Scientists do believe that long ago, our entire universe was microscopic, just like an atom. It's possible that the Big Bang had no cause, and certain effects in the microscopic realm don't need causes. The Big Bounce Theory. A cosmological theory for the origin of the known universe is called the Big Bounce. In the cyclic model or oscillatory universe interpretation of the Big Bang, where the first cosmic event was the consequence of the collapse of an earlier universe, it was initially proposed as a phase. Here's where the inflation theory comes into place. The inflation theory proposes that the cosmos had an exponentially rapid initial expansion. This theory was founded in the 1980s to resolve a number of issues with the conventional Big Bang hypothesis, which holds that the universe has expanded rather gently over time. However, some theorists believe that inflation was troublesome and unfalsifiable in the early 2000s because different parameters could be changed to match any observation, making the characteristics of the visible universe a matter of chance. So what did the Big Bounce theory and inflation theory result in? Well, according to the Big Bounce theory, the Big Bang marked the start of an expansionary phase that came after a contractive phase. According to this theory, there would be a big crunch and a big bang, or simply a big bounce. As a result, it is possible that we are living in any one of an endless number of universes, or that the one we are in now is the very first one. However, if the interval phase between bounces, which is thought to be the hypothesis of the primeval atom, is taken fully into account, then such enumeration may be meaningless, because that condition could represent a singularity in time at each instance, if such perpetual return was absolute and undifferentiated. The core element of the quantum theory of a big bounce is that the quantum form behaves differently as density approaches infinity. Even in a time period smaller than that which in measurement may never be possible, 1 unit of Planck time spanning or bracketing the point of inflection, all the so-called fundamental physical constants, including the speed of light in a vacuum, need not remain constant during a big crunch, looking past the singularity. So remember when we mentioned earlier that it all started from a point known as the singularity? Well, here's the answer to the question. We are well aware that the universe has been expanding and cooling since the Big Bang. However, it is tempting to go back in time before it all started. The cosmos was denser, hotter, and much smaller long ago. However, in mathematics, numbers can push the boundaries of the origin. This can take into account even the infinitely small dimensions, infinite densities, and infinite temperatures, or what is known as a singularity. Since the definition of this phase before the concept of space and time in the cosmos came into being, it was called the Big Bang. The Big Bang suggests that the universe used to be hotter, denser, more uniform, and smaller. It only possesses the characteristics that we observe now as a result of the length of time it has spent cooling, expanding, and being affected by gravitation. A smaller universe should have had radiation with shorter wavelengths, indicating higher energy and hotter temperatures because the wavelength of radiation extends as the universe expands. It was once so hot billions of years ago that even neutral atoms couldn't form without being blown apart. Even earlier than that, the energy content of the universe was dominated by today's microwave radiation, which was far more energetic than matter at the time. Atomic nuclei were quickly destroyed in earlier eras, and in even earlier ones were unable to produce stable protons and neutrons. Now you could assume that if we projected all the way back to arbitrarily hot temperatures, close proximity, and high densities, this would actually be the beginning. The entirety of the space that currently makes up our visible universe would be condensed down to a single point if you were willing to turn the clock back as far as you could. It is true that the rules of physics would fail under these extreme circumstances when compressing all the matter and energy existent into the universe as it exists now into a sufficiently small region of space. You could attempt to compute different attributes, but the results would be meaningless. A singularity is a set of circumstances where time and space have no significance. If you perform the arithmetic, it first seems as though a singularity is unavoidable, regardless of what dominates the energy content of the universe. As we can observe, the cosmos is more advanced now than it was then. We are also gazing further back in time as we gaze further back in space. The things we witness from that time period should thus be more recent, less gravitationally clumped, less massive, composed of fewer heavy elements, and have less developed structures. Even more than that, there should be no more stars or galaxies. There should remain a few leftovers, now cool and sparse, of cosmic radiation from this epoch from the radiation that was so hot that neutral atoms couldn't form steadily because the radiation would consistently knock any electrons off the nuclei that they were seeking to bond to. Big Bang nucleosynthesis suggests that there was an early, pre-stellar area where nuclear fusion would have taken place when it was so hot that even atomic nuclei would have been blown apart. As a result, we predict that before any stars formed, there was at least a small population of light elements and their isotopes dispersed throughout the cosmos. The ability to look back as far as the evidence will allow is a huge accomplishment for science. We are able to test our models, hypotheses, and understanding of the cosmos because the physics that occurred during the initial moments of the Big Bang left its mark on the universe. The universe's large-scale structure and the cosmic microwave background radiation, which is the remnant radiation from the Big Bang, are both affected by the cosmic neutrino background radiation, which is the universe's oldest discernible trace. Amazingly, this neutrino background radiation was there for only a fraction of a second after the hot Big Bang. However, extrapolating beyond the bounds of your quantifiable data is risky, though a luring game to play. After all, if we can go back 13.8 billion years to the Big Bang when the universe was just a fraction of a second old, what's the harm in going even further back to the singularity that was supposed to exist when the universe was 0 seconds old? Surprisingly, the response is that there is a great deal of harm. If you think that creating unsubstantiated, inaccurate assumptions about reality is detrimental. Beginning at a singularity at arbitrarily high temperatures, arbitrarily high densities, and arbitrarily small volumes will have effects on our universe that aren't always supported by evidence, which is why this is problematic. For instance, if the universe emerged from a singularity, it must have done so with precisely the proper amount of stuff, matter, and energy combined in it to balance the rate of expansion. Now, the initially expanding cosmos would have already recollapsed by now if there had been a teeny bit more matter, and if there had been just a little bit less, the cosmos would have grown far faster than it has now. The rate of the universe's initial expansion and the total amount of matter and energy present in it, however, are observed to be in perfect balance. Why? Well, we have no explanation if the Big Bang originated from a singularity. All we can say is that the cosmos was founded this way. Similar to this, we don't see any magnetic monopoles, which would be predicted to exist in a cosmos that experienced arbitrarily high temperatures. Even if the cosmos is seen to have identical temperatures everywhere with an accuracy of 99.99% or better, it would be predicted to have different temperatures in areas that are casually separated from one another, i.e. are in opposite directions in space from one another. We are always free to use the circumstances in the beginning as the basis for any explanation and to conclude that something is the way it is because of how the universe came into being. But as scientists, we're usually much more intrigued if we can identify a cause for the characteristics we notice. That and more is exactly what cosmic inflation provides for us. Yes, extend the hot Big Bang back to a really early, incredibly hot, incredibly dense, incredibly uniform state. But stop yourself before you travel all the way back to a singularity according to inflation. There must be a method to configure the cosmos such that the pace of expansion and the total amount of matter and energy are in balance. The same holds true for a universe with uniform temperatures everywhere. A slightly distinct point is that in order to prevent high-energy relics from forming, you must find a mechanism to eliminate any that may already exist while also preventing your world from ever being too hot. The same approach discovered by De Sitter back in 1917 is used by inflation to propose a time previous to the hot Big Bang when the universe was dominated by a big cosmological constant, or anything that acts similarly. By capping the highest temperature that can be achieved when inflation finishes and the hot Big Bang begins, this phase spreads the universe flat, gives it uniform qualities everywhere, eliminating any pre-existing high-energy remnants and stops us from creating new ones. It also generates fresh predictions for the kinds of flaws that cosmos would have at its beginning by supposing quantum fluctuations were formed and spread throughout the universe during inflation. Since inflation was proposed in the 1980s, it has been put to the test against the alternative, a universe that sprang from a singularity in a number of different ways. We discover the following when we stack the scorecard. There is nothing that the hot Big Bang can account for that inflation cannot also account for. Inflation reproduces all of its triumphs. The puzzles that we can effectively solve by stating starting circumstances in the hot Big Bang are explained by inflation. 4 of the predictions that can distinguish between a hot Big Bang without inflation and inflation have been tested with enough accuracy. Inflation is 4 for 4 on those 4 fronts, whereas the hot Big Bang is 0 for 4. But if we go back to our concept of the beginning, things start to become extremely fascinating. An inflationary world cannot be extended back to a singularity, but a universe with a matter and/or radiation, what we get with it, the hot Big Bang, can. Space will approach microscopic sizes, infinite temperatures, and infinite densities due to the exponential nature of its expansion. It will never achieve them. This indicates that inflation certainly cannot lead to a singularity on its own, as opposed to necessarily causing one. The instant we understood that an inflationary phase preceded the hot, dense, and matter and radiation-filled phase that we currently occupy, the notion that the universe originated from a singularity, and that's what the Big Bang was, had to be abandoned. 3 crucial facts regarding the universe's creation are revealed in this new image, which contradicts the conventional narrative that the majority of us were taught. First, the original theory of the hot Big Bang, according to which the universe erupted from a singularity that was infinitely hot, dense, and tiny, has since been expanding and cooling while being full of matter and radiation, is untrue. Although there is a limit to how far back in time we can extend the picture, it is still substantially accurate. Second, cosmic inflation has been clearly documented by observations as the condition that existed before the hot Big Bang. Any prior elements of the cosmos were figuratively inflated away during the early universe's exponential expansion phase before the hot Big Bang. When inflation came to an end, the cosmos overheated to a high temperature that was not arbitrary, giving rise to the hot, dense, and expanding universe that eventually developed into the one that we live in today. Finally, and probably most significantly, we no longer have any understanding or confidence regarding how the cosmos itself originated or even whether it did. By its very nature, inflation obliterates all knowledge that existed before up to the last few seconds, when it terminated and gave rise to our fiery Big Bang. A phase that did originate from a singularity may have come before inflation. It could have come before some other non-singular phase, or it could have come before inflation for all eternity. We have no option but to accept our ignorance until the day comes when we figure out how to extract more knowledge from the cosmos than currently appears to be feasible. Even though the Big Bang occurred a very long time ago, it wasn't the beginning as we all believed. So let us know your thoughts in the comment section below. Subscribe to our channel for more content like this, press the bell icon to never miss an upcoming update, and thank you for watching.